Welcome to the Module 15 Part 3 notes. In this section, we will look at how to do a hypothesis test for a mean. Module 12, the mean of the distribution of the sample mean is equal to the population mean. The standard error is the standard deviation of the population over the square root of n. The central limit theorem says our distribution is normal if we have a sample size of at least 30 or our population is known to be normal. And the z-score equation was the sample mean minus the mean of the distribution or the population mean divided by the standard error. So sigma over the square root of n. Now we have a problem with these notes, or not with these notes, with this z-score equation. It's going to be hard enough for us to know what the population mean is. It's going to be pretty much impossible for us to know what the standard deviation of the population is. So instead, what we're going to do is we are going to substitute the sample standard deviation for the population standard deviation. And that changes our distribution from the normal distribution to a t-distribution. And a t-score, which still tells you how far away from the mean you are, is as follows. You take your sample mean minus your population mean and divide that by the sample standard deviation over the square root of n. So now this t-distribution is still bell-shaped. It is still centered and symmetric about a t-score at 0, which is the mean. The total area under the curve is 1. But as the t-distribution gets closer to the normal distribution, so as the sample size increases, I said that wrong. As the sample size increases, the t-distribution gets closer to the normal. So what does this mean? Well, it means if I draw a normal curve, and I'm going to do it down here because we're not actually going to do this example. If I draw a normal curve, okay, looks something like that. Not exact, but close enough. A t-curve where I take a sample of 30 might look something like this. So with this distribution, the mean is still in the middle, but now it's a lot more squished and a lot more spread out. So there's a lot more area in these tails on the outsides, and there's a lot more variation from sample to sample. If I take a sample of 100, then the t-curve looks a little bit closer to the normal curve. And then finally, if I take a sample of size 1000, my t-curve is even closer. So the t-curve is going to change depending on the sample size. And we call this the degrees of freedom. And the degrees of freedom is equal to the sample size minus 1. So for what we're going to do with this hypothesis testing, we're going to need to know the degrees of freedom. And we're just going to need to remember that we're now using a t-distribution, not a normal curve. Because we don't know the population standard deviation. So we have to substitute the sample standard deviation instead. All right. So now examples 1 through 5 had you practicing how to read a t-distribution table. I am going to actually put this in Module 14 because we aren't going to need it in this section anymore since we're only doing the p-value approach. So go ahead and skip down to the p-value approach. So just as before, we are comparing the probability of the results from our sample to the level of significance. If the results from our sample are less likely than alpha, if our p-value is lower than alpha, then we reject the null hypothesis. Okay, and a fun rhyme to help you remember this. This works for proportions as well. If P low, reject HO. So if your p-value, your probability, is lower than alpha, you reject the null hypothesis. So 4 steps just as before, and we have to change one of them. So give the null and alternative hypothesis. That's going to stay the same. We're not going to draw the curve, though. Instead, we're going to verify normality. Verify that we have a normal distribution for step 2. Step 3, calculate the test statistic, which is a t-score, and the p-value, or the probability, for that test statistic, and then give the conclusion and interpret the results. So let's go ahead and get into an example. So we are interested in testing whether the mean age at onset of anorexia nervosa in young women has been decreasing. Assume that the previous mean age at onset was 15 years old. Data was gathered from 20 young women who were admitted for the eating disorder. Assuming the sampling distribution is normally distributed with a mean age of 14.251 years old and a sample standard deviation of 1.512 years old, test this with a level of significance of 0.05. Lots of information there, so let's highlight some important things. So mean age, that tells us that our null and alternative hypotheses are going to contain mu. The previous mean age was 15. We looked at 20 young women. The sampling distribution is normal. We have a sample mean of 14.251, a sample standard deviation of 1.512, and a level of significance of 0.05. So lots of information here. Go ahead and start in those 4. Woohoo! Ooh, there we go. Okay. All right, start with those 4 steps. So step 1, write the null and alternative hypotheses. So HO mu equals 15. The previous age was 15, so we're going to assume that the current age is 15. HA mu is, ooh, we didn't highlight that. Let's go highlight that. So we want to know if the mean age is decreasing, which means this is a left-tailed test. So we want to know if the mean age is now less than 15. All right, step 2, verify normality. The problem told us to assume normal per the problem. If this problem did not contain this sentence, we would not have a normal distribution because we only surveyed 20 women. In order for it to be normal, we have to have at least 30 women, or we have to be told that it's normal. In this case, we were told that it was normal. So we can go ahead and we can move on to our test statistic. T equals the sample mean, 14.251, minus the population mean, so what the value is for mu in the null hypothesis, divided by the sample standard deviation over the square root of the sample size, which is 20. So 14.251 minus 15 is 0.749, And the bottom piece is a very long number, 0.338 ... Use all those decimals. So negative 0.079 divided by 0.338093472, and we get negative 0. Oh, hold on. I did the wrong number. Negative 0.749 divided by this number. I apologize. It is negative 2, that didn't look right to me, 0.2154. All right, now we're going to learn about a new function in our calculator, and you'll be able to find it pretty quickly. So we need to calculate the probability of being less than, because it's a left tail test, so that means less than, negative 2.2154. But we can't use normal CDF because we're using the t-distribution, not the normal bell curve. So even though we're assuming a normal, we have to take into consideration that we used 1.512 in that t-score equation, and that is not the population standard deviation. So to calculate the probability with a t, we're going to use a function in our calculator called t-CDF. And this is in the same list where we found the normal and the binomial. So second vars, and then it's either the 5th or the 6th option, depending on what type of calculator you have. If you're using a TI-83, it is option number 5. If you are using a TI-84, it is option number 6. That's because the TI-84 has one more option than the TI-83s. And it's not a big deal. Okay. So now the first thing we need to put into t-CDF is where we want to start calculating probability. So just like with the normal, if we're looking at less than, we're going to start at negative 1 million, or negative infinity. We're going to stop at our z-score, negative 2.2154. And then the last thing it wants is the degrees of freedom. The degrees of freedom is your sample size minus 1. So in this case, our degrees of freedom is 19. And that's how your calculator knows which of the possible bell curves to calculate the probability for. Because as you change your sample size, your bell curve changes. So we go ahead and we do this, and we get, I apologize, my cats right now, y'all. They are being super crazy. One of them just jumped into the box very aggressively, and there goes the other one. All right, back to the notes. So we do our t-CDF, negative infinity, or negative a million, negative 2.2154, 19, and that gives us 0.0196. So the probability that we got a mean age of 14.251 is 0.0196. So we need to know, is this probability too small? Step 4. So is 0.0196 less than alpha, your level of significance? This is the only place alpha comes in, is when we're doing that comparison at the end. So is this true? Yes, it is. So if P is low, you reject HO. So reject the null and conclude that the mean age of onset of anorexia is less than, let me move the screen down, 15 years old. So that is your conclusion and your interpretation. Woo, cancel. All right. So here's our first hypothesis test for a mean. So write out your null and alternative. Look at whether the problem told you it's normal, or make sure you have a large enough sample size. Calculate the t-value. Find the probability associated with that t-value according to your alternative, less than, not equal to, or greater than. And then come to the conclusion and write out your interpretation. So this is how you solve a less than problem. An alternative that is less than. Go ahead, let's go to the next example. And we'll look at the greater than. Nope, this is not a greater than. This is, yeah. All right, so according to a study in 2010, the mean number of text messages sent and received by teenagers daily was 50. Suppose another researcher wanted to dispute this claim to see if the mean is different from 50. A simple random sample of 100 teenagers yields a sample mean of 47.75 texts with a standard deviation of 15. Perform the hypothesis test with a level of significance of 0.10. So what we're going to do is follow those same 4 steps. Step 1. Write the null and alternative hypothesis. Step 1. So our null, let's see if we can do this one without highlighting. No, let's not. Let's reverse for a second. Pause, reverse. Highlight important things. So the mean number of text message sent was 50. They want to see if the mean is different from 50. They sample 100 teenagers. Sample mean of 47.75. Standard deviation of 15. Level of significance of 0.1. That's everything we're going to need in order to solve this problem. Now we can write out our null and alternative. So our null, the mean, is equal to 50 because that's what the previous study said. Our alternative, the mean, is not equal to 50 because the other researcher wants to see if the mean is different from 50. So different means not equal to. Step 2, is this normal? We weren't told it's normal, but our sample size is 100, which is greater than or equal to 30, so it is in fact normal. Step 3, calculate that t-score. So t equals the sample mean, 47.75, minus the population mean, which is in the null hypothesis, 50, over the sample standard deviation divided by the square root of the sample size. So this is negative 2.25, right? I'm doubting myself right now for some reason. Negative 2.25. 15 divided by the square root of 100 is 1.5. So our t-value, our test statistic, is negative 1.5. Woo, there we go. Go back to that. So now we can calculate a probability with this test statistic. So we're going to use TCDF because this is a T, not a Z. And again, this is a two-tailed test, and we ended up with a negative Z-score. So we're going to treat this as if it's left-tailed and then multiply the answer by 2. If I had gotten a t-value of positive 1.5, I would treat this as if it's right-tailed and then multiply my answer by 2. So negative 1 million, negative 1.5, and then the degrees of freedom is 1 less than your sample size, so 99. So 1 less than whatever you put in the square root right here. All right, so let's go to our second vars. Go down to TCDF, negative 1 million, negative 1.5, 99, and we get 0.0684. And because this is a two-tailed test, we have to multiply that by 2. Wrong color, you're not going to be able to see that. 0.0684 times 2 is 0.1368. So now we can ask ourselves, for step 4, I have to write smaller, is 0.1368 less than, what was our level of significance? 0.1. No, it is not less than, so the probability is not too small. Therefore, we do not reject the null and conclude that the mean number of texts sent and received is not different from 50. So notice in these conclusions and interpretations, when I am not rejecting, I'm putting not whatever my alternative was. Do not reject. The mean number is not different from 50. If I come back up here to the first example, we did reject, so it is whatever the alternative was. So do not reject, not the alternative. We don't have enough evidence to say that the alternative is true. We don't have enough evidence to say the person is guilty. So we say that it is not false or not guilty. Okay. I'm not going to say that it's equal to 50. That's like saying the person's innocent. We're not going to do that. How many more times can I say not in this sentence before I confuse you? All right, one more example. Here we go. A bus company advertised a mean time of 150 minutes for a trip between two cities. A consumer group had reason to believe that the mean was more than 150 minutes. They sampled 40 trips and found a mean of 153 minutes with a standard deviation of 75 minutes. Test the hypothesis with a level of significance of 0.05. All right, step 1. Nope. Highlight. I almost forgot to highlight again. Zoom in a little bit. So they're advertising a mean time of 150. But the consumer group thinks that the mean is more than that. They sampled 40 trips. They found a mean of 153 minutes. They found a standard deviation of 7.5 minutes, and we're testing this with a level of significance of 0.05. All right, now we can get into step 1. Let me zoom back out so I have more room. Step 1, write your null and alternative hypotheses. So our null starts with an HO. We've got that mu is equal to the claim of 150 minutes. Our alternative is that mu is more than 150 minutes. They're saying, yo, you're telling me we're going to get there in 3 hours, but I'm thinking it's actually going to take us more than 3 hours. Okay? It's like if you ride a bus from Denver to Glenwood Springs. They say you'll get there in about 3 hours. I say, maybe not so much because I-70 is I-70. I think it's going to take longer. Okay? So now step 2, verify that it's normal. So we don't have anywhere in here that says the population is known to be normal or assume a normal population. So we have to look at our sample size. Our sample size is 40, which is greater than 30. So we're good. Quick check. That says normal, by the way. My R kind of got connected to my M. All right, now step 3. Calculate that t value. So the sample mean, 153, minus the population mean, which you'll find in your null, over the sample standard deviation, which is why we're using t, not z, over the square root of 40. This is 3 divided by a number that's not going to come out to an even number, 1.185854123. So 1.85 ... Go ahead and use all the decimals. 3 divided by my answer, 2.5298. All right, and now because this is a right-tailed test, we have this greater than symbol. We're going to treat this as if it's a greater than probability question. So T CDF. We're starting at our z-score. We're stopping at infinity. And our degrees of freedom is 1 less than our sample size, so 39. Calculate that. So 2.5298, 1,039,000, 0.0078. So is the probability of a trip that is 153 minutes too small? So step 4. Is 0.0078 less than 0.05? Yes, it is. Therefore, we reject the null. And conclude that the mean travel time is more than 150 minutes. So they were mistaken about the average time it takes to get from one city to another. It is actually more than 3 hours. So this is how you perform a hypothesis test by hand for a mean. I'm sorry. My mind just totally went blank. Hypothesis testing for a mean. So right-tailed. Woohoo! All right, try that again. Right-tailed, two-tailed, left-tailed. Looking at the t distribution. The calculator video I had actually previously recorded, and I talked about comparing to alpha over 2 with a two-tailed test. Go ahead and just completely disregard that. I recorded the calculator video way before, and so I made some changes to how I introduced the two-tailed test to you. So you're always comparing the probability to alpha, never alpha divided by 2. And that's because we took our probability and we multiplied it by 2. All right. So this is it for Module 15, Part 3.